I'm guessing most of you have heard about backpropagation. Maybe you've studied it, maybe you've done it. One can just say that backpropagation is an algorithm for computing the gradients of your neural network with respect to the parameters of your network. So we can sweep it all under the table as implementation detail. But when you use there's a few things. When you use the standard packages like TensorFlow or Torch, PyTorch, CNTK, they have a structure to them, and it's because of the way things like backprop work. So the reason for the structure and kind of the way to understand what's going on behind the scenes is all based on the way these gradients are computed, which is the backprop algorithm. And it's a way to organize the calculations to make the computation much more efficient. And also, as I mentioned earlier, when you have massive neural networks, to compute the gradient by hand and kind of code it up as a function could be kind of practically impossible. All right. So in essence, backpropagation is the chain rule. People say that a lot. Oh, backpropagation is just the chain rule. Well, that's kind of true. But when you want to actually implement it, you have to think through a lot of different cases to make sense of it. All right. So let's build up a bit. Let's talk about partial derivatives as a way to also visit some notation. So here's our computation graph. Here we're doing a vector input and a vector output. G is our function. And we can also break that up into components. So now I've broken up this vector into a bunch of scalars. So now we have p scalar inputs and n scalar outputs. We'll do one or the other depending on what we want to emphasize. So let's start with this. And let's consider the partial derivative. We can take the partial derivative of any of these outputs with respect to any of these inputs. Right? So we can write that down. So the partial derivative of like some ith output with respect to some jth input is going to tell us if we were to kind of imagine each of these inputs is controlled by some slider or some dial, right? And we picked some setting and we ran G and we got a bunch of outputs, right? And then we took, say, A2 and we nudged it up by an amount delta, right? So how much is, Bn going to change, roughly? It's going to change roughly by the partial derivative of Bn with respect to A2 times delta, times the amount you changed A2. That's how much you expect it to change by. So it's written here. OK, so that's kind of the meaning of the partial derivative. And what we're going to end up with our kind of neural network is we're trying to say for all of those many parameters that we're trying to tune, if we took any one of them and adjusted it by a little bit, how much is the final output going to change way down the road? Right? And that's what the partial derivative is, and that's what we're trying to get to. So let me skip this. OK. But we, of course, don't have just one function. When we lay it out in a neural network, we write this computation graph, and we have many functions composed with each other. Let's start with just two, G and F. So we have a vector of p scalars coming in, and we produce n output values, which are then fed into another function to finally produce another vector of m. Right? So it's altogether, this is representing the function f composed with g applied to a. Is that clear? OK. All right. And so the question is, what if we want to compute the partial derivative of a c, one of these c's, with respect to an a? All right. And the recipe for doing that, the theorem to do that, is called the chain rule. And the idea is very simple and perhaps intuitive. Let me leave that off for a second. So suppose we want to do the partial derivative of Cm with respect to A2. So if we tweak A2, that will in general have an effect on each of these B's, right? How much of an effect? The effect on B1 will be the partial of B1 with respect to A2. The effect on B2 will be the partial of B2 with respect to A2, and so on. So we can have like a first order approximation to the change of each of the B's from a change in A2. All right. And now F, we have the similar thing. If we're interested in the eventual impact on CM, we have the partial derivative of CM with respect to each of these B's. Right? And what the chain rule tells us is that if we want to know the effect of A2 on CM, we basically look at all the paths from A2 to CM and add the effects along each path. So the effect of A2 on CM through B1 would be the amount that a change in A2 affects B1, so that would be the partial derivative of B1 with respect to A2, times the partial derivative of CM with respect to B1. And then we add up over all the paths, so adding up over all the B's. So that's what's going on here. We're summing over all the B's, the partial of CI with respect to BK, times the partial of BK with respect to AJ. All right. Is that clear? So this is the core operation that's happening in backpropagation. So let's do a quick example. Let's consider least squares regression. And we're not going to define the backpropagation right away, but by working through examples, kind of warm up to it. So linear affine hypothesis space, we have a data set, we have our loss function for a single example, no regularization here yet. And so this is like SGD, where we're only considering one training point at a time, and we'll take a gradient step with respect to that. And so this is our gradient. So one kind of useful innovation that's relevant to whatever you want to implement that's very prominent in neural networks is with the computation graph, it's a nice way to break down your computation into different steps. And so if we were to do that for just this expression, which seems pretty simple, but we could actually break it down quite a bit. So we can define y hat to be this w transpose x plus b. That's our prediction. And then what next do we need? This difference, that's the residual, right? So we can take another step and say the residual r would be y minus y hat. And then finally, the loss would be just the square of the residual. So this is, you can view this loss as the composition of three different functions. So here's a computation graph corresponding to that. So we have, four things are inputs to this graph in some sense. The parameters w and b and the training data x and y. And in a sequence of computations, we compute the prediction score, the residual, and then the square of the residual, right? All right. So what do we want to do? We want to compute the derivative of L with respect to W and to B, and that'll be what we need. So the strategy is we start with L, and we compute its derivative with respect to R and Y hat, and then W. So we work our way from right to left. That's kind of the backpropagation strategy. So let's just do it very quickly. Partial L with respect to R. Yeah, 2R, good. And then partial L, okay. So partial L with respect to R is 2R. Partial L with respect to Y hat is what? Now we have some chain rule to do. Partial L with respect to R, and then R with respect to Y hat. There's only one path from Y hat to L, so there's no summation, right? Good. So, and this is 2R, and partial R with respect to Y hat is -1. Great, okay. And then partial L with respect to W is what? Let's do some chain rule first. So what should I do the partial with respect to? Yeah, well, we could do Y hat, because we already have, so we could do partial with respect to Y hat. We could have done r, but then we have to work our way further. So y hat takes us closer. And then partial y hat with respect to w. What's partial y hat? Well, let's keep it simple and take a particular entry of w. W is a vector, right? So let's say w sub j. Okay, so that's minus 2r for the first piece, and then partial y with respect to w sub j, x sub j. Yeah. Great. And something similar for b. So we work our way from right to left. All right. Let's do ridge regression. So same thing, but we're going to add in a regularization term. So we have this regularization piece, and then we usually call j the final objective. So we're going to add this regularization piece into the objective. Here it is as the computation graph. You see now there's this extra piece. So coming off w, we have this other path now that feeds into the final term. So the challenge is going to be, what do we do for w? So I'm going to skip these pretty straightforward. But the issue is we kind of have two different paths to get to w. So let's just zoom into that issue. This is kind of a simplified version of what's going on in the other graph, because we have something feeding into two different nodes. So I think it's very helpful to think about writing two different independent copies of A. And so, because right now, if you write, it would be helpful to know how much does J change when we change this input here, but not this one. But it's confusing because A leads to both of them, so can you really change one without the other? So you can. I mean, it just makes them different. So I find it helpful to introduce kind of temporary placeholders for two different copies of A. And then we can talk about, we could say that partial of J with respect to A, so this guy, is the sum of the two different routes to get from A to J. One is the upper one and the other is the lower one. And so we have partial J with respect to the top copy of A, and the derivative of A, that's A1 with respect to A, and then derivative of J with respect to the bottom copy of A, and partial of the bottom copy with respect to A. Right? So of course, these derivatives, derivative of the copy with respect to the A, those are each 1. Right? And so they drop out. And so we see that if you want to know how much J changes, what the derivative of J is with respect to A, we can look at derivative of J with respect to the input to F, and derivative of J with respect to the input of G, and we add them. All right. Okay. All right. So let's work on the ridge then. All right. So in the previous, when we saw this graph previously, we figured out partial of J with respect to y hat. And that remains the same. Had that. And then we can ask, what's the partial of J with respect to this copy of W, the W that gets fed into W transpose X plus B. And the idea is that you can imagine, we would imagine, if we tweak just this input, but leave the other copy of W the same and every other value the same, not the values downstream of W2, but all the other things not on the path between W2 and the final output, how much does this change to W2 impact J? And that would be the partial derivative of J with respect to this W2. So that's easy by a chain rule. It's the partial of J with respect to y hat times the partial of y hat with respect to W2. Let's look at the jth component of W2, so that would be xj. Right? let's write that out. So just j with respect to y hat times xj. And then for w1, what's that derivative? Partial j with respect to say the jth component. So LW transpose W is LWI squared. Basically, I equals 1 to, I think D is my dimension. I forget. All right. J with respect to WI, let's trace through the graph. That's J with respect to R times R with respect to WJ1. What's partial J with respect to R? 1, trivially. And R with respect to the jth component of WI1. We differentiate this. It's just with respect to W. Oh, I left something off here, huh? So that's just going to be 2 lambda. Say again?
No x.
No x?
Right, it's your.
Oh, thank you. Thank you. Got it. Great. Thank you. Good? Great. Okay. All right. Okay. And then finally, how do we figure out the partial j with respect to W, the original W? Just sum them, that's right. You sum along all the paths coming out of W. Great. All right. That's essentially the hardest part of backpropagation, is handling the situation where a single parameter feeds into multiple nodes. A lot of treatments gloss over that, but that's kind of, the whole thing isn't too hard, but in backprop, that's the harder part. All right. So that's it for a specific example, and then I was going to try to just give a slide or two on how to think about backprop as an algorithm on the whole. So general backprop. So as we said, think about it as a specific way to evaluate the partial derivative with respect to j, the final output of the network, with respect to the output and the input of every node in the graph. You really only need the partial derivative with respect to the parameters that you're going to do gradient descent on. But the algorithm will eventually give you the partials with respect to inputs and outputs of every node. Yeah?
Sorry, would you mind going back to that diagram?
This guy?
So the training example has y going into the heart of our network here?
Yeah, the training example enters right there. Yeah. Mm-hmm. The training label.
But this isn't like an issue from a test, train, deploy, because all I get out of this is my W's and B's, and then I can bring those to production, and I will be able to predict.
Oh, I understand what you're saying. 1 second. Okay, right. So this computation graph is a graph for computing our objective function. We will pull a subgraph of this graph to actually do a prediction. Do you see what subgraph we would choose? Yeah, this is a great point. I wish I could draw on the slide now and circle this piece as a piece of the graph that would bring to production, because that is making the predictions. That's right. So in a neural network, multilayer perceptron, this part would have much more going on. Lots of layers, lots of nonlinear transformations. So this would be a much bigger piece of the computation. Here it's just pretty trivial affine transformation. And then, so in a multilayer perceptron with classification, for instance, all this stuff that has to do with the loss and the regularization would be a small fraction of the full computation graph. Here it dominates it. That's interesting. Yeah. All right. Okay. So the way I think about backpropagation is that it's the thing that works node by node. So you visit one node at a time, and you run an operation called backward on a particular node. And the prerequisite to running backward on a node is that you've already run backward on all of the children and descendants of the node. So all the things that a particular node feeds to, you have to have already run backward on that. And we'll say what. And then what does backward do? Backward at a node f, if you think of f as taking input A and output B, backward returns the partial derivative of the final objective function j with respect to both the input and the output. So it returns partial j with respect to b and partial j with respect to a. All right. Okay. So here's the simple case. This is kind of maybe a zoom in of the network where we're interested in f. This is the node we're working on now, f. And f has some output, it feeds into a bunch of stuff, and then maybe we've absorbed a whole bunch of more nodes into a single node called h. Maybe g's absorb a lot of stuff. But the general point is that this can summarize anything that can be downstream of f, between output of f and the final output j. All right. So if we're ready to do backprop for node f, and to keep things simple for now, for this slide, we're going to consider a and b just scalars, and then we'll go back and do the vector version. So a and b are scalars. So what do we need to run backward on f? The assumption is that everything downstream of it has already run backward, which means we know the partial derivative of j with respect to the inputs and outputs of each of these nodes. In particular, we need the partial j with respect to each of these inputs. So that's this input. So partial j with respect to all the different copies of the output b. And then what would the output be of backward on f? We need two things. Backward delivers the partial j with respect to b. Let's start there. How do we figure out the partial of j with respect to b, given the partials that we got as input? Sum them. Yeah. That's that was the essence of the argument we made before. So we have all these paths to go from b to j, and we sum the partials of j with respect to each of the copies of b. Okay. So yes, the partial j with respect to b is this sum over the partial of j's with respect to all these copies of b, all those b inputs. And then we need the partial of j with respect to the input a. And there, that's just straight chain rule. So the partial of j with respect to a is j with respect to b times b with respect to a. Right? Straightforward. So when you call a node, it's going to pull in all the derivatives from its children, add them together, and then it'll combine that with the local derivative. You can think of the local derivative as the derivative of b with respect to a, and the output with respect to the input. Okay. When you use a neural network framework, they have infrastructure for making these computation graphs, and you can create a new node type, a new function type or something. And what you're responsible for doing is these sorts of computations. So you need to know how to compute if you have the derivative of j with respect to your output, how do you get the derivative of j with respect to your input? And that's the thing that you have to work out. This part is standard. You're always going to sum these things. So there's nothing special going on here. The framework can take care of this piece for you. In fact, in the lab that Pierre and Philip put together, this part's taken care of for you, the summing piece. But this you still have to handle. All right. So now let's consider a and b as vectors, as is more standard. And it's, again, the same. We just break out b by each of its components, and then we sum the partials for that component. And this part becomes a little bit more interesting because now for a particular AI, that can influence each of these g's through many b's. Right? So now we suddenly have whatever the dimension of b is, little n. We have n different paths through which any particular component of I can influence the g's. So we just sum over all those paths. So we're summing over little n, that's how big b is. and we have the partial of, so we have the partial of j with respect to a particular component of b, and then that component of b with respect to the AI that you're differentiating with respect to. So this is kind of in all paths happening inside here, because A can affect each of these B's separately. And that's it for the kind of the core backprop equations. How do we run this thing? Well, we had to guarantee that each backward was called on a particular node only after all of its children have already had backward called on them, so you have the prerequisites. So there's something called a topological sort for a directed graph, directed acyclic graph. So you can't have any cycles, directed cycles, or you can't have a topological sort. But so topological sort is an ordering of the nodes so that every node is before its child node. Right? So we need like the reverse of the topological sort order because we need the children to be evaluated before the parent. So you get a topological sort, and then you call backward on each of your nodes in the reverse topological sort order. And this last part is what the framework we provide will support. And then the internals of the nodes is what you would do for your part. Yeah, so any questions on backpropagation? That's pretty much it. The devil's in the details a little bit. You've got to do some calculations to get the local parts. So to work out expressions to evaluate for this piece can take some work, especially when you start doing things like mini batching, where you have a whole matrix of input x's to handle, and you eventually, this is all component-wise, but of course that's not very efficient. So once you work out your expressions for the component-wise partial derivatives, this is just a scalar, you probably want to figure out how to repackage things together so it's vectorized and matrix vector operations. And for typical examples, this is not too difficult, but after kind of investigating many different ways to present computing these derivatives, I found that the easiest really is to go component-wise and then put it back together. This is in contrast to the beginning of this course. I was talking about how to take derivatives with respect to vectors at a time and stuff like that. And that's great in those scenarios, but it actually gets too complicated here because you have to, in that case, differentiate with respect to matrices at a time, and it gets a bit hectic.
So,
yeah.
So for the ReLU function, since it's not differentiable, do we take subgradient and apply the same method?
Okay, I like this question a lot. So what do you do for the ReLU, which is not actually differentiable? It's got a kink in it. It's not differentiable at that point. So what people generally do is, where you would do a gradient of ReLU, replace it with a subgradient. So yeah, what you said. The sneaky thing, though, is that it's probably not fresh in your mind, but in the definition of subgradient is that your function is convex. A subgradient is defined for convex functions. So ReLU is convex, so you could talk about the subgradient of ReLU. But the neural network is not convex. So if you just run backpropagation, using your subgradient of ReLU at each spot, it's not like what you're ending up with is a subgradient of your function. Your function is not subdifferentiable. So it's not exactly clear with our infrastructure what the heck we've just computed. But in any case, that's what people use in practice.
And the depth of the neural network, will it affect, it will increase the complexity of computing the subgradient by a lot of amount and the number of nodes in a single layer, right? So is that a determining factor? Is backpropagation a determining factor for how much deep the...
You mean computational complexity? Yeah, so computational issues is definitely So this is another piece of folk wisdom for you, which is that make your network as large as you can afford to do the computation for. So with the regularization techniques we've discussed, dropout or weight decay or whatever, kind of the folk wisdom is that you will always do better in generalization with larger networks, which does not really follow naturally from the types of discussion we've been having in this course. But this is just one of the mysteries. It's still a mystery, I'd say, of neural networks. And so what's the takeaway is, if you can afford the time, make your network bigger. That's the advice people tend to give. More questions? Yeah.
What's feed forward?
Oh, so feed forward, the multilayer perceptron that we discussed as the key example of neural network is a feed forward network. There's also what's called RNNs, recurrent neural networks, which is, I guess, in opposition to feed forward. You can draw it in a way that looks like it has feedback, but really, when you come right down to it, you can unroll a recurrent neural network into something that is a feed-forward network. So I'm not sure there's some fundamental difference that I know of. An RNN would be something like this. This is like an input. You'd use an RNN for like sequence input or something. So you have your input could be a sequence of words, and your output could classify, I don't know, whether it's grammatically correct or not. A silly, arbitrary example. And maybe you encode your words as bag of words, right? And so your input could be xi, which is the bag of words encoding, and then you have another layer that does something, and another layer that does something. And this is like a slice that recurs. So you could maybe write it like this, something like this. And the idea is that when you get multiple words, so if your input is just the house, this representation becomes, here's one slice, and then you repeat the slice for the next word, and these kind of self-pointing arrows just map from one to the next in the time slice. So it always unrolls into something that's kind of feed forward. Anyway, what else? Yeah?
Can you comment, so for problems where the regular least square do a good job, do you have something to say about the performance of neural networks compared to other regular techniques? So I understand that neural networks have the advantage that they can tackle a very large class of problems, it's very expressive, but case where we have a pretty good technique with regular least square.
So like a linear model, you're doing regression, you have a linear model, it does well.
Yes. And do you think a neural network would do just as well, better, worse? My intuition is that it's a little bit worse.
So your intuition is that the neural network may do worse because maybe it'll overfit or something like that?
Because it would take a long time to solve a very easy problem.
Oh, in that sense, yeah. Yeah, the time to converge and perhaps the amount of data it needs to converge may be quite a bit higher. The time to converge certainly would be higher. So in that sense, performance would be better with a smaller model. But if we're talking about the eventual generalization performance, I mean, I would also like to say that linear model will do better, but I can't. I don't know. I mean, you have to imagine that there's some nonlinear component in your data, probably, unless it's artificial data. With enough data, I mean, I think we could safely say that with enough data, the neural network will always be at least as good. It might be a heck of a lot slower,